Good evening, everyone, and shout out to our students over in the Middle East, to Anwar and Ratsman as well, who is joining us for the first time this semester. Okay, so just going to hang on for another couple of minutes to kind of wait for people after their work in Malaysia to join. So today is not a lecture per se, but it's a Q&A session. I'd like to go over any of the concepts that, on your self-study if you found it difficult to follow. So I'll be happy to go over them. Yeah, so just hang on for a little bit to wait for people to come in. So I think everybody is familiar with the UlearnX platform. This is what you should see. And then this is the starting point. Looking at this guide here, I've uploaded the introductory session. This was conducted on the 13th of May. And so today's session also recorded will be uploaded here. The focus would be on the key understanding of the MOSFET switch networks, the current capacitance relationship. So at this point in the course, we are roughly 5 weeks into the program, roughly, and the course should end by end of July, so roughly about another month and 3/4, 1.5 months left to go. So this one, introductory parts on what is VLSI, the whole design process flow, some open source tools for you to play around with. We'll talk about parasitic extraction later and the wires and the model later. You should have completed all the videos under module 1. So if you click on here, right, and if you follow the links, there are a bunch of videos here. You can click here to go to the next video, and then you can click at this point to actually download. Just a very rough set of slides I used to prepare these videos. So you should have completed up to this point. The module 1, the module 2, and the module 3, and should probably be almost done with the assignment 1 from the West and Harris chapter 1. These are the 5 questions. Chapter 2, these are the 4 questions, and chapter 2 here, and another 4 questions. And then starting soon, we can go into the delay and the variability, reliability, and aging. But today is just more of a cap to just take an overview of how everyone is learning well the charge voltage, current voltage relationship, and the switch network model of digital logic. Okay, let's see who has joined us. So we have 14, we are roughly 3 minutes into our session. Maybe I'll wait another 2 minutes and then we can start to take questions from anyone from among the audience. Okay, so I guess I'll get started right now. So welcome everyone, and please feel free to interrupt me at any time to let me know how your learning is progressing. Okay, so the goal of this session actually is to touch base, check with all of you how you following the material. Are there any doubts, any confusion on the reading material, on the assignments, anything that you're not able to solve, anything that you are stuck with? And just to get you a little bit warmed up, I will start to give some general overview on some of the topics, but just feel free to interrupt me at any point because your questions have the priority, right? Okay, let me just turn on my whiteboard here. Okay. Right, so we're talking about VLSI, and VLSI stands for Very Large Scale Integration. And when we talk about VLSI, we are mostly concerned with digital logic. That is, sometimes you've learned in the undergraduate, this is the ones and zeros that you can compute to make, computation and all that, right? But what we're concerned with is once that ones and zeros have been converted into digital logic gates, and then you translate those digital logic gates into actual transistor implementations where you, where you really have maybe this kind of transistors that you've probably seen in the textbook. You have maybe a block of silicon here. You would probably dope this with N-type material, dope this with N-type material, then this may be a P-type block, and then you put a dielectric layer here. Typically, it's silicon dioxide. Then there is a conductive layer here. Used to be metal. Nowadays, it's actually polysilicon. It's also a doped silicon layer. And this forms a MOSFET, metal oxide semiconductor field effect transistor. Very fancy name, but the key point is just as described in the video, you apply a voltage here. All the free electrons floating in the P region will actually accumulate underneath the channel to form a conducting channel here. So that allows us to actually conduct current across this. And then if you remove this voltage here, then the channel no longer becomes conducting. And so the whole point of this course is to see how the digital logic is implemented with these as our basic building blocks. And the first step to see is we are actually approximating these logic gates as a digital switch. Okay, so this is a symbol of a switch. And in particular, this digital switch is a voltage controlled switch, right? And this is called CMOS, or complementary metal oxide semiconductor technologies, because you actually would build the digital logic from a pair of complementary gates, pair of complementary transistors. So this is the most basic, the most basic configuration. I have my VDD here, and then I've connected to one switch, and this switch is a PMOS transistor. I will denote it with a circle on the label here, and then this is an NMOS transistor. I denote it this way, so it's a bit ugly drawing, but let me try it again. Okay, this is what the circuit schematic looks like.
Doctor, I cannot see your drawing.
You cannot see my drawing.
My laptop problem.
Okay, anyone else has a challenge not able to see the, oh, okay, I'm sorry, let me try that again. I think I might not be sharing.
Yeah, can, but need to zoom out.
Need to zoom out, that means I have to zoom in a bit more. Okay.
Yeah, now okay.
Okay, yeah. Okay, so what I was, okay, let me just draw that again. Okay, thanks for highlighting that. So let me erase this. Okay, so the first basic concept is basically how do you assemble digital logic gates from these basic transistors. That's the first step that the first part, chapter 1, that is basically covering, right? And it's this idea that we are going to actually assemble the logic gates using pair of switches. Okay, that's why it's called complementary metal oxide semiconductor, right? So you have a switch that is a PMOS transistor, and you have a switch that's an NMOS transistor. So this is what a switch network looks like, such that if this switch is closed and this switch is open, okay, so if I close this switch, this output here is tied to VDD. Okay, this is a logic 1, so VDD can be 1.1 volts, 1.8 volts. It depends on whatever technology you are using. And if you were to then use the voltage to open this switch, and then you end up shutting this switch. The output is then connected to ground, so it's logic 0 here. Okay, so the equivalent of this circuit, right, in the MOS, the CMOS symbols is something like this. Okay, so this is your most basic circuit. This is equivalent to your inverter. Okay, so this is how you tend to learn to draw your logic gates in undergraduate. You use symbols like this, or this is like for your AND gate. This is like for your OR gate. And you also have versions called NAND gate and NOR gate like this. Okay, and this is how we assemble them using complementary transistors. So bear in mind, there are various ways you can build a digital logic gate, right? So there's a logic called the NMOS logic, right? So this is a resistor, and this is a NMOS transistor, and this is VDD. You can build logic gates like this as well, but nobody does this anymore. Why? Because this is always sinking current. This is a huge power sink. It's not efficient for devices. The reason this works is because at any one time, one of the transistors will be closed, that means you'll be conducting, and the other transistor will be open, not conducting. And so when your logic gate is actually holding a logic 1 or logic 0 state, in its steady state when it's holding, there's no current flowing, there's no power dissipation. Later on, you'll see that, yes, there is actually some, but in general, to the first order, there's no power dissipation. So CMOS logic has the advantage that it's actually a little bit of a current saving mechanism. And it's like, if you're familiar with push-pull drivers in the motor circuit, it's a little bit of something like that. So one switch will be closed, one switch will be open. And then if you flip the logic, one switch will be open, the other switch will be closed. And so the way we would learn how to assemble logic gates, the NOT gate being the simplest, is we think about them as a pair of complementary switches. When one is closed, one is open. So let's go ahead and see how we would derive the complementary switch network for this NAND gate. So the first step would be we would try to write the truth table. So this is the input and this is the output. So the truth table is just a mapping of the input logic levels to the output logic levels. For a NOT gate, input of 0 will give logic 1, input of 1 will give a logic 0 at the output. So logic 0, of course, is ground, and logic 1, of course, is VDD. So for the NAND gate, you got two inputs, input 1, input 2, and the output. So you get 0, 0, 0, 1, 1, 0, 1, 1. So it is not an AND gate, which means that this is the logic. That means your AND gate, when two of them are logic 1, you usually get logic 1 here at the output and everything on zeros. But this is not an AND gate. It's the opposite of an AND gate. So this is the logic level, right? So we must find a way to devise a circuit where when both the inputs are logic 1, that means the switches are logic 1, it will be connected to 0. So how we draw the switch network, we have two switches here connected to 0. So this is the output here. So two switches in series. And then you have two complementary switches in parallel here. And both these switches are connected to VDD. And this switch is the inverse of this switch, and this switch will be inverted with this switch. Okay, so if you close this switch will be open. 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 This is the complementary metal oxide semiconductor logic. That means there has to be one NMOS paired with one PMOS transistor. So the equivalent circuit be something like this. And VDD. And this is the output where you're reading the voltage. Okay. And you can then check the logic operations. When this is 0, that means this switch is conducting. This 0, this switch is conducting. If both of these switches are conducting, the output is being pulled up to VDD. If either one of these switches is conducting, right, in either this switch and this switch not, it's always pulled up to 0. Only when both these switches are not conducting, that is when they have a VDD here and a VDD here, and these two switches are conducting, do you get this output pulled down to logic 0. And this will be the same for the NOR gate. And so the first competency, the first skill you would need to develop is to be able to see quite quickly, to be able to kind of memorize and remember, how do you assemble this basic NOT gate, NAND gate, NOR gate out of complementary MOSFETs this way. And we approximate the MOSFETs, the first instance, by a switch. And this also tells you something very interesting because you are not limited to 2 input gates. You can actually devise a 3 input or 4 input or a 5 input NAND gate, right? So this is a 2 input NAND gate. If I wanted to have a 3 input NAND gate, or maybe a 4 input NAND gate, for example, I could just have 4 transistors this way, and then I could just have 4 PMOS this way, connect them up. And this one is tied to the first input. This one is tied to the second input. This one is tied to the third input. This one is tied to the fourth input. Everything goes to VDD. And so now you start to realize that you are not limited to the 2 input AND and OR gates that may be in your digital electronics course as an undergraduate. You were limited to this. You can design a whole plethora of different gate configurations, right? So starting with the NAND and the NOR and the NOT gate. And you can have multiple inputs, outputs. And the text and some of the reference material also shows you other kinds of interesting gates, such as the AOI, OAI. You can have buffers. So this is AND or NOT, AND or invert. This is OR and invert. So it's actually implementing the product of sums and the sum of products from your digital logic implementation. You also can have something called the majority gate, where the gate is actually trying to determine if there's at least out of an odd number of inputs, if the majority are logic 1, then the majority gate will give a logic 1. Then you have a minority gate and so on. So there could be very custom designed gates which are more efficient to implement with CMOS logic, complementary MOSFET logic, and these form a basic set of logic gates which are available to you at the design. And normally this collection of logic gates that is made available to you is called a technology library. And a technology library is basically a set of pre-designed logic gates that the fabrication, sort of like Taiwan Semiconductor Manufacturing or SMIC in China. So these are the fabs, the places where they would actually make the silicon chips. Intel will have its own fabrication facilities as well. So these would be the places where they actually make the chips, but they have actually developed the specific recipe for each of these individual transistors, how they connect, and the timing and energy properties of all these basic gates. There'll be an array of gates that is made available to you of different sizes, and all those gates that are made available to you is known as a technology library. And in ASIC terms, you call this your standard cells, right? Because they are standard cells, standard logic cells, from which you'll be constructing your gates. And you probably have heard of maybe people talking about, oh, I've implemented my chip in a 7 nanometer technology or a 16 nanometer technology. That simply refers to a particular recipe for constructing gates. And that 7, 16 nanometer, 100 nanometer actually refers to the length. Roughly speaking, it refers to the length of the channel from this point to this point. That's not strictly true in today's nanometer size gates, because the gates now what happened, the logic, the transistors now what happened is you don't actually have a flat channel. The channel is actually going something like this, and then this is your doping, and these are actually known as FinFETs, or sometimes they call them 3D MOSFETs, right? So what happens is instead of a straight flat channel, right, and a straight flat gate, the gate is actually this, three-dimensional, this kind of three-dimensional rectangle here. It's got a very high form factor, and the channel will actually be formed across here like that, from this part here all the way going up, coming down like that. And this distance is your 7 nanometer, 14 nanometer, 16 nanometer, and so on. Okay, right. So at this point, just kind of taking a quick survey. Are you all okay? Do you understand the process of constructing digital logic gates with switch networks and then converting that into CMOS networks? That means a network of complementary NMOS and PMOS transistors. Okay, so if any questions, just interrupt me. Otherwise, I'll just kind of go on and kind of cover what would be the main materials that you should be responsible for. Okay, so now I presume you have a good understanding, or you're developing your understanding of uh, how to assemble basic logic gates, how to understand how they are basically assembled. And we're going to be moving on a little bit further. So from your understanding of how the MOSFET, the complementary MOSFETs are kind of connected, the next step is to see how you can lay this device out on a wafer. So there's a wafer like this, and usually this wafer is what is...
Excuse me, doctor.
I'm sorry?
Doctor, can you explain the multiplexer using CMOS?
Ah, that's a great question, Khadijato. Okay, the multiplexer actually has several implementations. So let me go through two of the more popular ones. We start by first defining the truth table, and I would like to actually encourage you to start always with the truth table, at least at the beginning, right? And the multiplexer is one of the examples of what we call a complete digital logic family. So I'll give you an example of one complete digital logic family. If you have a NOT gate, you have an AND gate, you have an AND gate, and you have an OR gate. You only need these three sets of gates to build any combination of logic circuits. Any combination, only this set of gates forms a complete logic family. Alternatively, if you have a NAND gate and a NOR gate, you only need these two logic gates to implement any combinational logic. This holds for whether it's an integrated circuit, whether it's a discrete digital logic that you build from chips. This is called a complete logic family. And a multiplexer on its own is also a complete logic family, because I can show you how I can implement an AND gate and an OR gate, an AND gate, OR gate, and NAND, and an AND gate, OR gate, and NOT gate using a multiplexer. So this is a multiplexer. What it does is there's a control bit here. If the bit is set to 0, whatever is at this input I0 gets sent to this output. If the control bit is set as 1, whatever is at this I1 gets sent to this output. So you can think about this multiplexer as implementing if and else operation, but with a digital circuit, right? Because the if and else condition is set by this condition bit, and what's being sent at this output here, I0. So if C equals 1, I1 is sent to the output. And if C equals 0, I0 is sent to the output. Now, this multiplexer, of course, we can implement it as a sum of products. This is the most basic form you probably have learned in digital electronics as an undergraduate. Okay, so I can put I0 here and I1 here, and this is my out. Okay, and this is my control, and this is my control bar, right? So the only way I can send I1 to this output here is if C1 is a logic 1. If C1 is a logic 0, this NAND gate effectively, this AND gate is effectively like frozen, right? Because it's only going to hold a 0 at the output as long as C is 0. Conversely, if C is 0, so C bar will be 1, then this value here would be dependent on the value of I0, right? So this AND two-stage logic, an AND gate followed by an OR gate, is an implementation of a two-input multiplexer. Of course, you sort of realize also that multiplexers can also be created from 2-bit control. So it would be equivalent to a 4-bit multiplexer. You can have an 8-bit multiplexer, in which case there are 3 control pins and 16 and 32 and so on and so forth. So you can implement them as a sequence of AND and OR gates. Now, if I were to put in a so if you were to use De Morgan's law, De Morgan's law rule is a rule for actually inserting knots here. So if you put De Morgan's rule, I can actually put an inversion here, an inversion here, an inversion here, an inversion here, and that would make it equivalent. So let me delete this first. For some reason, this thing is always coming up today. Very annoying. Okay. And why I'm putting this inversion is because this now then becomes equivalent to a two-stage NAND gate. So I'm basically kind of reviewing a lot of material very quickly to show you first that a two-input multiplexer can be implemented as a cascade of AND gate followed by OR gate. This is called the sum of products, right? You are summing, right? These all functions associated with plus, and then the products associated with AND gates. And any sum of products, SOP, can be implemented equivalently as a two-stage NAND. Right, two-layer NAND, and of course we've seen just now the NAND gate basically looks like this in CMOS. Right, so this is the first stage output. So this input, right, this input here corresponds to maybe this terminal here. This input here corresponds to this terminal here. This is an output. This output goes into the input terminal of a second stage NAND gate like this. Okay, so we're building this up from basic building blocks. Now, of course, this is a very canonical, straightforward, simple to understand way of building multiplexers. There are actually faster multiplexers than this, and that would be the example of what we call pass transistors or pass gates. And the way you can think about pass gates are something like this. Remember that we said a MOSFET is equivalent to a switch. Okay, so if I put a logic level here and I set this to be the control pin, if the control pin here, the gate here is a logic 1, the channel is formed here, so this is conducting at the output, and if I set it to logic 0, this channel is not conducting. So if I were to do something like this, sorry, let me. This is channel with a NOT gate, and this is channel. So this will be I1 and this will be I0. I can read this output. This actually forms a multiplexer because when the channel, when the control bit is set as logic 1, there's a channel forming here. Whatever logic value that I put in at this input will be passed to this output here. I don't really care about this because when this is logic 0, this transistor acts as an open circuited switch. So whatever voltage is sitting here does not get transmitted here. Only this path is conducting. And likewise, when this is set at logic 0, this path is not conducting. There's no channel here. But if this is set at logic 0, there's a logic 1 going out of this NOT gate is enabling the path here, is selecting this path. But this is just an implementation of NMOS. And remember, we are implementing CMOS. So CMOS requires a complementary transistor here, as well as a complementary PMOS going through here, right? So drawing's pretty bad. Let me just draw it again. So I'm basically connecting two transistors like this. And this is known as a pass gate, right? So when you have two of these in parallel, okay, so I have two of these in parallel, and I connect their outputs together, I tie them up together. This forms a 2-input multiplexer. If I get a 4-input multiplexer, I can tie 1, 2, 3, 4 of them together, driving the same output. 8-input multiplexer, and so on and so forth. And immediately you can sort of gather that this is a more probably efficient, smaller, power efficient implementation, because the number of transistors you use is basically 2 times the number of input channels, whereas if you were to implement it as a 1, 2, 3 input, three NAND gate structure, you would use something like 12 transistors for just a 2-input multiplexer, right? So Kadira Jato, does that answer your question? Is that helpful?
So basically, what you are saying that every time I want to create a multiplexer, I'll be using the NMOS and PMOS, both of them, connected in parallel?
That is one way you can be using it. You can also use a multiplexer with this configuration. There will be certain instances where you'd favor this selection, and there are certain instances where this will be a little bit more acceptable. To a first order, if you're not going into IC design, it actually doesn't matter to you. To a first order, you can choose either one. If you are going into IC design, then it matters a little bit because of something we call the pull strength. So I'm just going to explain it a little bit just for the benefit. If you get it, great. If you don't be overly concerned. But if you want to learn it as well, then that's okay. So the pull strength regards to the fact that if this is a logic 1, it's a MOSFET. If this is a logic 1, then a very strong channel is formed here, and this MOSFET quickly creates a channel and is conducting. But when you put a logic 0 here, what happens is this channel gets disabled or disconnected rather slowly. So this is called a weak pull-up situation for the CMOS, for an NMOS transistor. This is why you need to put the PMOS in parallel. Because in the situation when this is experiencing a strong pull-up, that means it's able to really establish the channel very quickly, this PMOS is actually in a weak state. That means if you leave it alone, let's say if you put in a logic 1 here, and you put in a logic 1 here, a logic 1 on this PMOS to disable it is going to result in a kind of a slow switching of this PMOS, but it's going to result in a fast switching of this NMOS. So you have them in complementary. It's because the fast switching will be enabled by this one, and then the slow switching, it will compensate for the slow switching of the PMOS when it's a logic 1, and when there's a logic 0 here, the PMOS will be the one that's switching quickly, and the NMOS will be one that was switching slowly. So that's the reason for actually having the complementary structure here. This one is kind of light in the sense that you are actually sort of allowing the voltage to propagate here, but the problem is there's going to be a slight voltage drop here across these transistors, just as you get an accumulated voltage drop here. And the problem is also when you start adding all these gates together here, you will soon see that the capacitance on this node here rapidly becomes very big. It's going to be linear with the number of inputs here, whereas on this point here, it's probably also the same, but there'll be going to be certain ways you could size this transistor. But this one is quite favored because it's kind of small and light implementation of it. But you have to be a bit careful, especially if you do multiple layers of multiplexer. So this is just one parallel multiplexer, but you can also implement a multiplexer as something like this, you know, a cascaded multiplexer, set of multiplexers. And if you use the pass transistor to cascade it that way, after 4, 5, 6 layers, the voltage drop across the logic can actually start to add up. So if you have only like 1.1 volt, you know, and you're dropping maybe 0.1 volt here, after like four in series, you would actually lose like 0.4 volts and your voltage headroom isn't so great anymore. Whereas if you're using something like this, that headroom is essentially a little bit better preserved. So there's pros and cons of when you would use one architecture, one assembly versus another, but that's only if you're in the IC design and if you are just going to go really deep into these selections. At the first order, I think for general knowledge, it's good enough to know that these are the ways you can assemble a transistor into logic gates. That should be good enough. All right.
Okay, thank you, doctor.
Okay, great question. Thank you. So just recapping, one of the first competencies for you to develop will be to understand how you can assemble logic gates, digital logic gates, using complementary metal oxide semiconductor. So you think about them as switch networks, a pair of complementary switches. One is an NMOS transistor, one is a PMOS transistor. How do you assemble them in various configurations like the multiplexer, like the NAND gate, NOR gate, NOT gate? And just how do you start to think about them? Because why that's important is because quite rapidly we will move to using these schematics, these arrangements to estimate the delay, the speed possible to be achieved by any digital circuit. This includes digital integrated circuits and all that. So we're moving towards that. So we're building on the fundamentals. The first steps for you to understand how these transistors are assembled. And since you know the topology, how they're connected, you can start to see that we start with a silicon plate. So let me try to delete all of this. Okay, so apparently I'm still not so good at. I have to figure out how to delete the whole whiteboard. Okay. Right. So we start with the silicon wafer. It's a kind of a flat piece of, well, silicon is literally derived from sand, and it's polished and it's in a lattice structure and it's polished to be a really, really flat piece. That's why it looks reflective like a mirror. And what happens is this silicon, there will be certain atoms that are implanted in them. And the reason you implant them is because you want there to be free electrons that are kind of floating around, or free holes if this is a p-type, right? And then what you do is you get a special kind of tool that would actually kind of have a small patch here to be implanted with a different type of material, let's say an N-doped material, for instance. Then you could have another region here, which is an N-doped material, and then you would then use a mask. You would dope silicon dioxide here. That's dielectric insulator, and then you deposit like a metal connective layer here. So that forms one transistor, and you then have another region here, P layer. You dope a bigger region here, N, and you dope P-type material here, dope P-type material here. You have your insulator built here, kind of added here. Then you have your connection here, and then you sort of run the connection over the top. And this would actually form your, and you've also run another connection here. And then this would be connected to those kind of traces that then connects to a huge pad. And then you put your VDD supply here. This will be connected to a big huge trace, and this will be connected to the ground. And voila, this is how we build up the individual logic gates on the silicon wafer, except that this is drawn really large and all that. In actual fact, the actual dimension size of this is on the order of nanometers, right? And typically the sort of dimensions we're looking at, roughly speaking, this is known as L and this is known as W. So the length of the transistor, right, is channel length, right? This is given by L, and typically this is the smallest number in the process. If it's a 7 nanometer process, this is roughly 7 nanometers. If it's a 0.180 micron process, this is 180 nanometers. And this width is a parameter that the designer has some degree of freedom to control. Why? As we will soon see, width and length are some of the design parameters for you to control the current that is flowing through the transistor. You call it the drive strength of the transistor, right? Because we are doing all our computations with voltage and current. So we apply certain voltages, logic 1, logic 0, and then there's current that's actually being conducted through the transistors, the MOSFET transistors, and the capacity of that MOSFET transistors to drive the current is directly related to the speed of the device. Let me repeat that. We care about current is because the greater the current your MOSFET can actually source, can actually handle, the faster your device will be, right? There's a relationship there. The problem with that is you can't have arbitrary large currents. I mean, you can't be running a digital circuit with like 2 amps, 3 amps of current. That's just too much current. You don't need that much current to do the computation. So it's a power draw, it's a power hog, right? So in modern devices like your mobile phone, you're talking about battery life, which means you really want to drop the current draw as low as possible. So you've got these two competing trade-offs, whereby you actually want the current to be larger so that the device can operate and compute faster. The logic gates will switch faster, but you also want the current to be low so that you can actually get more power savings. You can consume less power for the same computation, for the same type of computation. So that's the perennial challenge. And it's important for us to understand two relationships. That is the relationship of the current to be a function of voltage, for example, VGS, that is the voltage put in at the gate, and the relationship of the capacitance, right, to be a function of, again, VGS, VDS, right? So back to this transistor, this is the gate, this is the drain, this is the source. Now, remember, we always talked about putting an oxide layer here, and then you have a metal conductor here. This oxide layer is an insulator, and guess what? You have a conductive layer, insulating layer, conductive layer, conductive layer, insulating layer, conductive layer. This forms a capacitance, right? And the capacitance, the basic equation for the capacitance is proportional to the area. That means this part here, the area here. So what is the area here? The area is actually corresponds to the length times the width of the transistor divided by the distance, the oxide thickness. How thick is the oxide layer you're growing? And then some dielectric coefficient, right? And this is a material property. This is a property of the geometry, the size of your transistor. So I have the ability to change the capacitance of my transistor here. Okay. And I have some ability to manage the current, right? So the real relationship is mu Cox W over 2L. I think it's VGS minus VTH squared. So this is what we call the long channel model. But the key point I want to show you this is because okay, what? The key point for showing you this is because you can see the current is proportional to the dimension of the device. Okay, I grow the width of the device. I use a larger device that is growing in this dimension. I will get a larger drive current. And it's inversely proportional to the length of the device. So this is why we like to go to smaller technology nodes because my digital logic gates would automatically consume less current the smaller I make them, right? And it's also dependent on the oxide, the capacitance across this. That's C ox here. And mu is actually a property of the material. It's actually the mobility of the charge carriers within the material. If you're from semiconductor physics background, we can talk about that a little bit more. And VGS is the voltage applied to the gate here. And VTH is this kind of minimum barrier, minimum potential difference barrier that you have to overcome in order to start pulling the charge, either the electrons or the holes, to form a conductive layer. So this is kind of like the minimum threshold that you need to apply a voltage here before a very, very thin conducting layer improves. So you can see that the current is proportional to the square of the voltage here. So if you have a choice, if you want to increase current, it's actually much better to use a slightly higher voltage here because that gives you a squaring in the current value, and rather than you would go for a larger transistor size. Okay, so that's what this basic equation tells us. But there is a section in the book that talks about what we call the short channel effects, and those are the modifications to this equation or this relationship when the channel here becomes really, really short. That means it becomes really, really short. That means it's probably looking something like this. It's really short here, like 14 nanometers and so on. And that's the case. That has actually been the case for us for the last 10 to 15 years. We are in the short channel domain. And the key understanding, the key finding in the short channel domain is really that the current is no longer dependent on the square of VGS. It is approximately dependent on alpha, where alpha is quite close to 1. So the current now is almost linear with VGS, with the drive voltage here. Okay, so there is a corresponding weakening of the transistor drive strength as we scale, as we go down to smaller and smaller transistors to build our devices. So that's the important point there. And later on in the parts of the course where we would start estimating delay and all that, we'll see that that has an effect because we'll be looking at the sensitivity of current and how it changes with all these parameters. But the key point here is that when we go to very short channels, which is the scenario for the last 10, 15 years, it's no longer dependent on the square of the voltage. It's more likely to be dependent on the some power of alpha. Alpha is about 1.2, 1.3. So it's almost linear dependence on VGS. And the physical reason for this is something called the velocity saturation and mobility degradation. So the channel is so short, and you are doping it so highly, right? Because you want to really get as much carriers and electrons as possible, that those free electrons moving in that channel, they kind of are basically knocking against other electrons, and that sort of like reduces their effective speed. And there's also so that's the mobility degradation, and there's also something called the velocity saturation. Is that because you apply a voltage here, the voltage is like 1 volt, 1.1 volt, but if you actually look at the electric field, which is a ratio over the actual distance here, the electric field is really, really high. It's on the order of thousands of volts per region, and that electric field is sort of putting in a very strong force, pushing the carriers very close to the surface. So it's like the carriers are trying to move in this dimension, but they're sort of being slammed vertically in this way, and that sort of slows down their velocity as well. So this is the velocity saturation effect. A very brief description of what is elaborated in more detail in the text, right? So, but the key point here is to understand that this square dependence on the drive current on the voltage is no longer true in the short channel regime. And it's also important to understand the relationship of the capacitance to the voltage. Okay, so where are we going with this? So the key point of learning all these models, being able to compute them, is to build our toolbox to actually get the following model. So you would have the facility of the ability to just draw this kind of models here. And what we're essentially going to be doing in the coming weeks, you'll be learning is you want to now approximate this transistor as a resistance. How can you do that? Well, you have a relationship between I, which is the current flowing through here, and this is the relationship with VGS, but there's also another relationship, mu C ox over L, I think it's VGS minus VTH, and VDS over 2. So VDS is actually the voltage from this node to this node. So if you look at it, I have a relationship of the current through this transistor versus the voltage across this transistor. So if I draw the transistor as a black box, I have a relationship between the current and the voltage here. So what is the relationship between current and voltage? It's a resistance. So I'm able, using this curve, this relationship here, which can actually be plotted as a curve, right? I over VDS, you get a curve that looks like this. A bunch of curves, right? And this is the curve at the value of maybe VGS equals 0.5 volts. This is VGS maybe equals 1 volt, VGS 2 volts and all that. But basically you get this curve, and the slope of this curve at this particular point or this particular point is the inverse of the resistance here. So we are basically moving towards a point where you can calculate all these, you have a good understanding of these curves, you can basically estimate the effective resistance of this PMOS transistor. And then there's going to be another effective resistance here. Okay. And then we've been talking about this capacitance. So when we talk about capacitance, what are we referring to? Well, referring to you have your, let's say again, my PMOS, my NMOS, N well, N well, P well. So we've already gone through that there is a capacitance here, okay, capacitance from this point to ground. So that would mean that there's a capacitance sitting here to ground, right? And that's this part here. But if you look at this, what is N? N is basically a region where there are a lot of free electrons. What else has free electrons? Metal. And if you apply some voltage here, you also have from semiconductor physics, there is a very, very thin PN junction here, which means there's a very, very thin layer around the surface here where there is no electrons at the boundary here. And there's in this region here, you also have electrons. So what I'm trying to say is that you have a region of free electrons here, a region of free electrons here, and an insulating region in between. That insulating region is not something you put in, is not a dielectric. It just arises from the fact that you have an N-type material bordering a P-type material. Automatically, there is a charge-free region that forms at the interface. This acts as a capacitance. So at this part of the gate, this part here, that appears to be a capacitance sitting here, just as there appears to be a capacitance also sitting here. So we are essentially moving towards a model where we convert your MOSFET into an equivalent resistance R, and then there is a capacitance to ground here sitting at this terminal, and it's also the sum of the capacitance sitting at this terminal of the MOSFET, so the sum will be here. And what is this? This is a resistive capacitive network. We can use this as an effective charge and discharge of the capacitance to estimate the delay of logic gates. That's where we're going with this. This is the whole reason for you to really learn and understand the relationship between I and V, C and V. And to make matters a little worse, this C, the capacitance that is seen here, is not a fixed capacitance. It really depends on the value of VGS and VDS here. And so let me just briefly show you that section in the textbook where it's found. So if you go to the text and you go to the diffusion capacitance model. So the capacitance sitting at the drain and the source, these are what is known as the diffusion capacitance, right? Because this is the diffused, the capacitance is coming from diffuse region. So this is just ways to calculate it from some more basic material properties. So these are all parameters that give you the material property. Roughly, if you want an order of magnitude estimate, you can look at where is it? Yes, here. So CO is sort of the gate capacitance, the total capacitance from the gate to the bulk. There's capacitance sitting at the input of the MOSFET, right? So roughly you can look at the capacitance sitting at the source and the drain somewhere in the region of either between half to almost 2/3 of the gate capacitance. So roughly sometimes we wave our hand, we say if you want a cost estimate, you take the gate capacitance, that would actually be equivalent to the source capacitance and the drain capacitance. But here the point is that depending on the voltage you apply to the gate, right, the MOSFET will be in different mode, either in cut-off mode, linear mode, saturation mode. And depending on the voltage you put here and the voltage across here, the effective capacitance on all these terminals will change. So you have a situation where the capacitance is dynamic. And this is the reason why you would probably need SPICE simulators to really get a good estimate of kind of the speed and the circuit switching. If you need that, because the capacitance all changes as a function of VGS and VDS. So this is something for you to be aware of. But when we do the circuit estimates, the delay estimate with the circuits, we're just going to assume it's a constant value, almost equivalent to the gate capacitance, right? So that's the main point from this that I wanted to highlight. But this is just giving you closing that loop so that you can really understand how the capacitance are computed and how they are modeled. But where we're going with this, as I mentioned, our desire to really model the switch transistor networks, the logic gates, as resistive and capacitive elements so that we can estimate the speed of switching these devices using the RC time constant. So from your basic electrical circuit analysis, you can actually infer that. Okay. All right, are there any questions so far on this material, on these parts here? There's quite a bit of text to read in the book and all that, so just go through that. You are probably not required to memorize that because all the exams will be open book, so you should just be able to reference it where and when you need it, but probably try to just get some practice through the assignments, the homework assignments, to just compute the values at least once in your life so that you just know where they come from. Yeah. Okay, so just pause for a little while to see if there are any questions, any doubts on the IV characteristics and the CV characteristics, and why it's important to learn this because of where we're going with to model the delay of logic circuits.
Sorry, Dr. Kim, I have another question.
Sure, that's good.
Temperature. I see sometimes they talk about room temperature, at room temperature, and sometimes when they increase the temperature. Could you explain that a little bit?
Sure. Great. Another great question. So thank you for that. Okay, so let me just erase my board here for a little bit. Let me thank you for that. Okay, all semiconductor devices are by default temperature dependent devices. Okay, so there's something to keep in mind. Why? Because when we talk about semiconductor device, let me just go a little bit, make a little segue into basic semiconductor physics. So I get a slab of semiconductors here, okay? And it's called a semiconductor because there are already no free carriers there, right? And you want to contrast this to a metal, right? When you talk about metal, you basically have a lot of free electrons just kind of floating around, so that if you were to just attach this portion here to positive voltage and here to a ground, these free electrons will just be swept and they will move by what we know as drift current. drift current. Okay. In a semiconductor, this doesn't happen, but a little bit of magic sort of happens. Sorry, in a semiconductor, this happens because there are sort of some free electrons floating around, okay, in just a basic silicon or a basic gallium arsenide or a basic germanium slab. But the number of free electrons will be significantly less than the ones here. And there is an equation that governs the sort of a way that we experimentally try to explain the quantity of the free electrons here. Basically, what's really happened is the world is actually, your surrounding is actually present at a particular temperature, right? So if you're probably in Saudi or Qatar, it might be a little bit hot on that side, 40 plus degrees Celsius, 50 even heat, reaching heat 50, right? So temperature is just an indicator of the heat energy that's available in the environment. So what's really happening is the heat that's sort of just available in the environment that is measured by temperature. That heat, that energy can be randomly absorbed by electrons bound to the molecules here. Okay, so these are semiconductor semiconducting material. So we're talking about silicon, for instance, right? So this is silicon atoms, and the silicon atoms would have electrons that are bound to it, and then there's just a bunch that are just freely available, moving around. It's because from the environment there is heat that can be just sort of randomly absorbed by these electrons. So the electrons basically have a certain energy level. When they are able to absorb heat to exceed the energy level, they are able to break free of the attractive force of the atom, and then they become free electrons in the silicon device, in the silicon slab, okay, in the semiconducting slab. And the reason I'm really emphasizing this point is if you bring your semiconductor material, not we're talking about device, just talking about material slab. If you bring it into a region with higher temperature, let's say you put it into an oven where it's 100 degrees Celsius, that just means you're putting it in an environment where there's more energy available to be absorbed by the electrons, and therefore there'll be many more electrons that are able to absorb the energy and have sufficient energy to escape the capture of these silicon atoms, and they can be moving around, and they are known as free carriers. So there is a relationship between the temperature and the available free carriers in the semiconductor device. And this relationship is something that is exponential. Basically, it's actually given by the Maxwell-Boltzmann equation distribution. Okay, so there's a particular distribution. You can pretty much estimate what will be the quantity of free electrons at a particular temperature, right? So this is the temperature dependence. Now, what we tend to do in semiconductor devices is we kind of want to control the current by using voltage. So if you look at the silicon device here, the number of free electrons is really not that much. It's nowhere as much as the metal here. So we play a little trick. We say if we were just to insert impurities in the silicon, that's why we start with very pure silicon, a lattice, a semiconductor lattice. That's why it's got a mirror-like finish, right? But what happens during the fabrication process is we play a little trick. We intentionally disrupt the regular periodic lattice structure of this material by injecting impurities into that region. So there's a small patch, small volume where we inject impurities. And when we inject impurities, these impurities sort of end up in between the lattices of the silicon. And it has the effect of either dislodging some electrons or creating some additional voids or locations where electrons can get trapped, right? Can get held at, right? So the voids are called holes. And if you dislodge, then you have electrons, right? So this is an artificial way of increasing in a controlled manner, number of free electrons in the silicon, right? So we dope impurities, we insert impurities as a technique, as a trick to really increase the number of free electrons. Why? Because we're disrupting the lattice structure. We're intentionally using a material with sort of different number of electrons. So things are not balanced, then the excess electrons kind of flow out and become free electrons, and that do not require this temperature to escape the bonds, right? So our devices are designed on this idea that we add impurities to control the number of electrons, right? So that's why we can sort of calculate that particular voltage. What is the current, right? Because we have the total number of free electrons within our control by the doping mechanism. Now here's where the temperature becomes really tricky. This is silicon, and it's got a really, really high melting temperature. I think it's in the range of thousands of degrees Celsius. So I can raise this silicon to 500 degrees Celsius and nothing would happen to the material, except for the fact that the number of free electrons in this undoped region could rapidly rise to such a point where it could actually swamp the number of free electrons that are artificially created in the n-doped regions. So if you're in a situation, an extreme situation where you just run your semiconductor device, right, my MOSFET transistor in the region where the temperature is so high that you can't really tell apart the p-dope and the n-dope region, what you essentially have is a slab of silicon with undifferentiated regions. That means your device fails to function as a MOSFET because it doesn't look like a MOSFET anymore. What is a MOSFET? A MOSFET is a region where there's a high concentration of electrons here, free electrons, a high concentration of free electrons here, and a very, very low, almost no concentration of free electrons here. But when you apply a voltage here, whatever free electrons, few free electrons that are in the material will instantly get attracted to form that conducting channel. But if suppose you raise the temperature so high that there's so many free electrons here, this is no longer a MOSFET. So this is the destructive part of how temperature can really, really mess things up, right? Because it's really, really messing up your calculations in terms of that planned ratio of electrons here, right? So there is a temperature dependence on the number of free electrons in these materials. We are using doping, that means randomly, not randomly, but purposefully inserting impurities into the material in order to control the number of free electrons. But there is that wildcard factor. If that temperature rises above a certain amount, electrons will be released from the silicon material and then they will change the properties of your device. Okay, so not just this can happen when your temperature, like your room temperature, is 500, or we put this in an oven. This can also happen if you are running this device with a very high current. So if you're running at a very high current, it either means that, so current I is rate of change of charge over time. It can either mean that your charge is flowing very quickly or you've got a lot of charge here. So guess what? Current I squared R, if there's a resistance, this generates heat. So if there is a high surge in current here, there's high local heat here, the temperature at this junction elevates, the device can also go into that mode where it fails to become a MOSFET. This is why all transistors have a temperature limit at which you can operate them on. Room temperature, as well as sometimes you come across what's called the junction temperature. The junction temperature is literally the temperature at the edge, the boundary of the PN junction of the device, right? So that temperature heating effect can come from the environment. It can also come from the local heating due to the current that's flowing in this, right? So that's the temperature effect. And typically that temperature effect will have some kind of dependence, exponential dependence on voltage, and then there's the Boltzmann constant, and then there's the temperature. So there's an it's almost in semiconductor materials, in transistors, you would have to expect that there's this exponential relationship with temperature. So it's not a small linear relationship. It's like if you increase your temperature a little bit, you get rapid increases in the number of free carriers. So that's what you have to watch out for. And that's where the origin of the temperature comes in, why it's affecting the semiconductor. So this is a first order effect. Now there is a second order effect. The second order effect happens when because you're in an elevated temperature, the electrons have more energy. They're kind of not staying still, they meander around a little bit more. So if you happen to be driving current in this direction, the electrons that are flowing this direction will tend to kind of be repulsed more frequently by local electrons around there. So the temperature is actually having an effect on the speed or the mobility, not really the speed, but the mobility, the ease at which electrons can be pushed from one end of the material to another. This is called the mobility. So mobility in the device also has a temperature dependence. The higher the temperature, the more scattering of electrons happens. That's actually, like, the electrons kind of being attracted by the potential difference, but because they are nearby electrons, they are meandering, it will actually come into close contact with the electron and then gets repulsed, and then, it's just moving and meandering in the larger path. So the average time it takes to cross here is actually higher. So it takes more time to cross here. So this is modeled as a reduction in the mobility of the device, of the electrons, the carriers in this device. So temperature also has an effect on the mobility of this. And this is where you can see, back to that current equation, mu C ox W over 2L VGS minus VTH squared. There is a temperature dependence here. And yeah, pretty much is this part here. And also in this part here, at some point in the saturation, the velocity saturation regime, this alpha is going to be closer to this is going to be closer to 1.2, 1.3 thereabouts. But the temperature dependence of the current is actually going to be here. The T is coming in by influencing the mu here. So Kadichato, I hope I answered the question. If there's something I missed, please let me know.
No.
Okay, great. Okay, so this is kind of useful to understand because well, it's kind of a summary of the backstory from microelectronics physics. I try to piece it all together because we will be relying very heavily on these equations to estimate our delay, our performance in terms of delay of the logic gates. So it'll be good to understand where the model comes from, and don't take these equations like a ground truth. You need to understand that these equations were experimentally derived, meaning that, you know, this factor of 1.2, 1.3, 1.1, this is actually fitted from data, right? So it just gives us a sense of how the current is varying with all the geometrical parameters, right? These are geometrical parameters, electrical parameters, and material parameters mu here. Oh, there's another place where temperature will have an effect, that is on the threshold voltage. That is the minimum voltage that is required to establish a channel, a conducting channel on the MOSFET, right? So that the temperature effect will also come into play in the control or the changing of VTH, the minimum voltage required to establish that channel. All right. I'm going to pause for a minute here to see if there are any further questions on any of the materials so far before I will jump into something a little bit more new to set the tone for the coming week or so of your studies. Yeah. Okay, now let me tie together the big picture. So we've been talking at a fairly low level, single logic gates, going down to switch networks and then pairs of complementary PMOS, NMOS, and all the way to the device physics of that. But how does this relate actually to digital circuits? Because the course is properly entitled VLSI systems design. And, you know, when we do complex digital systems, we don't talk about individual logic gates. In fact, you talk about hundreds of millions of logic gates and above, right? So this is how it all ties together. In digital logic, I would say almost all our circuits have this form. You have flip-flop and you have what we call any kind of combinational logic. And this combinational logic is actually feeding the next state into the D flip-flop, and the D flip-flop is recognizing that state. So you can think about the D flip-flop as storing the mode, the configuration, the computational mode of this particular circuit. And the state is actually dependent on certain inputs and also the past state value. And this is all synchronized by clock. Of course, there's not one D flip-flop. There are hundreds, thousands, millions of D flip-flops. This is just sort of a conceptual diagram to kind of point out the fact that all our modern digital circuits, all actually have some kind of form where it's going to be a D flip-flop followed by combinational logic, followed by D flip-flop, followed by combinational logic, followed by D flip-flop, so on. All digital logic looks like this. And of course, if this is dependent only on the state, this is known as a Moore machine, and this will be your outputs. But if this is also dependent on the input, then it's known as a mini machine. And then I can, of course, insert memory, RAM, or ROM, and this can also fit into my combinational logic with addressing and all that, right? Things can get pretty complicated this way, but it's the first, just highlight to you the fact that all digital logic, all modern logic, no matter the most complex microprocessor today to the simplest LSI logic, it's always some combinational logic interspersed with D flip-flops. And of course, this combinational logic, you can always express it in terms of all the inputs, input 1, 2, input 3, input 4, and then you would have this particular state output. Let's call this state output 1, 2, 3, 4. You can build a truth table. You can have all your combinations of ones and zeros. Given the combinations of ones and zeros here, you can convert this into its logic form. But the key point is basically we are always designing synchronous machines. Okay. This is a local computation. It's a logic computation. These are the inputs. These are all the possible mapping of inputs mapped to an output combination. This is a local computation. And this local computational unit is synchronized with the activity of this local computational unit through a clock, right? Where does the synchronization happen? If it's an edge-triggered flip-flop, the synchronization happens at the edges. So in this case, positive edges, or if you got the negative edges, it happens at negative edges. Why? Because it doesn't really matter how, well, but it matters. Let me take that back. It matters. We'll talk about that pretty soon. But you have a little bit of slop, right? What I'm trying to say is that this can actually compute maybe in like 10 nanoseconds, and this can actually compute like, let's say 8 nanoseconds, right? They don't actually have to compute and arrive at their results at exactly the same time. Just as long as when these D flip-flops capture the computational value here, they capture it at the same time, the results are available there. So this synchronization mechanism of the D flip-flops actually makes it kind of easier to analyze basically what are limitations of the circuit and all that. Why? Because where I'm going with this is that you'll have a whole bunch of combinational logics being synchronized by D flip-flops. And there is a maximum clock speed at which you can run the entire design, right? So your clock speed has a period, T, okay? And there is a minimum period at which you can run this design. And if you try to actually have the clock come in at a faster period, that means the switching happens faster, this design will fail. And if you want to try to assess what is this fastest period at which I can synchronize all this computation, you need to look at the propagation delay through this block. You need to look at the propagation delay through this block. You need to look at the propagation delay through this block. And you need to look at the propagation delay through this combinational block. So this, if the delay is TPD1, the delay is TPD2, the delay is TPD3, the delay is TPD4. The clock duration is actually set by the maximum of TPD1, TPD2, TPD3, TPD4. So in other words, we are actually looking at the longest, the unit with the longest computational delay, and that sets the lower bound on the computational speed. That is the how often, how quickly are the computational results synchronized, and that is the clock period. Do you follow this explanation? It's a very important one. Okay, I trust that if you don't, you will raise a question, or if you happen to be watching this in the recording mode, you can also raise the question on WhatsApp. That's fine as well. Yeah, that's what the class WhatsApp group is for. So I'm introducing the concept that it pays for us when we're investigating the delay of a complex circuit. We need to find what is known as the critical path. The critical path is simply investigating all these local blocks of logic. Okay, which path of the combinational logic has the longest delay? Because that combinational logic path will set the maximum clock frequency. And if you can speed that maximum, that critical path up, you speed up the whole circuit. So our analysis, instead of looking at each and every logic path of the circuit, we understand that digital logic circuits are always smaller groups of combinational logic interspersed or feeding into D flip-flops. And we're looking at the digital logic in the region between two subsequent D flip-flops, all of them in the circuit. And each of these blocks, we're trying to find where is the logic path with the longest delay. And overall, for the entire circuit, there's going to be one or two or three paths or few paths where that is the path with the longest propagation delay. And what we're saying is that for the purpose of analyzing the speed, sometimes we call it the delay of the circuit, which is a measure of performance, right? Because we always want to have circuits that are high speed. We always talk about high speed microprocessors and all that. For the purpose of assessing the delay, it is sufficient for us to focus our attention on the critical path. So the first skill is really to look at a complex circuit and figure out what is your critical path. And the critical path is always combinational logic alone, right? So although we build sequential circuits, right? Sequential circuits, more machine, milli machines, but as I've shown you, tried to explain, and if you don't understand this, let me know. We really have to make sure that you understand this really clearly. A sequential machine is nothing else but combinational logic that you design interspersed between D flip-flops. That's a sequential machine. So really, we're back to studying just the critical path in all the small groups of combinational logic in the circuit. We pick the critical path and we evaluate it. We estimate the delay for that. That sets the fastest speed at which the circuit can operate on. And if we want to try to make the circuit go faster, we need to optimize the critical path to speed it up. Okay, so where we're going with this, there'll be some complex design that maybe it could be something like this, and then not gate and all that, and then something like this, right? So there will be a particular logic pathway, maybe the evaluation of this path here, going through 1, 2 gate, 3 gate, 4 gate, 5 gate, right? So this path here is going to be longer. It takes more time, right? Because the computation has to pass through this set of transistors first, then this set of transistors, then this one, as opposed to this path. This path is just very quick, right? It just goes through one gate, right? So this is actually the critical path in this complex logic sequence, right? This combinational logic. So we have to look at this logic from this block, from this block, from this block, from this block, from all the combinational blocks between the flip-flops. We find one path which is the longest delay. We study that path, we optimize that path. That is enough to help us to mitigate or reduce the delay of our circuit. So where we'll be going with this, remember we had our switch network model of the logic gates. Okay. And this switch network you can actually draw like a chain of this transistor NMOS, PMOS, CMOS gates, a chain to mimic this, and then these transistors will be kind of approximated by resistance and capacitances, and we'll be looking at evaluating the RC time constant, the effective RC time constant for all these to change state, right? Because the switching of a logic gate can be interpreted as the charging and discharging of the capacitance at the output of the logic gate through the effective resistance of the PMOS or NMOS. So that's where we're going with this. So this is all connecting the next set of topics you will study on the delay estimation. This is where we're going with it, right? First, identify the critical path, then learn how to estimate the delay using a formalism known as logical effort, right? Okay, I'm going to take a little pause at this point just to check if there are any questions and how people are doing with the material so far. So you're going to have to pick up the pace of your learning at this point. I think if you can cover the delay estimation with logical effort in the next 1 or 2 weeks, then we'll be in good shape by the end of June to start the variation and the aging aspects of the analysis. So how that would be, I'm just going to make a very brief mention about this, but if you don't get this, don't worry, we will cover it in a future discussion and Q&A session. We're going to be doing the analysis on the critical path, and process variations will introduce multiple near critical paths that may become the critical path after you do the fabrication, because you can't control with absolute certainty the device that you make. And aging, also similar approach if you created a device, a complex integrated circuit, when you use it over time, there will be a gradual slowing down of the speed of different parts of the circuit because of phenomena known as aging. There are 3 phenomena, distinct phenomena that have been identified. We'll discuss them. And that can be analyzed from the perspective of changing or lengthening the critical path of a circuit. So this concept of a critical path of our digital circuit is essential because it is how we are using a fair quantitative measure to evaluate the speed of our digital circuit. All right? Okay, so I take a pause to see if there are any questions. Any questions at all about your learning thus far and how are things going? Yeah. Okay, thank you for the feedback, Anwar. So I had another feedback from Amma. Thanks for the feedback. Okay, I'm just going to hang around here until maybe 11 p.m. to see if there are anyone with questions. But if you have no questions and if you'd like to kind of leave the session, you're welcome to do so. This session today has been recorded. I'll upload it shortly after our session today at 11. But I'll just kind of hang around and chat with people if anyone has more questions. And you're welcome to also hang around if you want to just join and listen in on any of your classmates' questions. So just wait a little bit. I'll be fine-tuning your problem-based assignments in the coming days. Basically, when will be your next session? Okay, I'm actually targeting it about 2 weeks from now. But Khadijato, if you need another session soon, if you're kind of stuck with your learning or you have more questions, feel free to post in the group and say, yeah, I need a session, or and then I'll just take a poll on people. If there are enough people that want to attend the session, then we can actually have a session next week as well, because it's probably better if it's kind of we have sessions that are that come after you've learned significant part of the material. So in principle, I'll be targeting the next session 2 weeks from now. But if you need an additional session or you want to have a discussion next week, just so you can catch up or you want to speed up the learning, feel free to propose it in the WhatsApp group. I presume all of you have access to that. If you do not have access to that, let me know, send an email. and then we can also schedule, right? So typically, I think it would be decent if we give people about 2 to 3 days to kind of schedule. I don't think it's too bad because you know, we seem to be going along the lines that we'll be having the schedule on Tuesday. So if you kind of figure out by Friday or Thursday this week that, you know, it's really something burning you want to discuss, you can let me know. Maybe Friday, Saturday, I'll send out a poll on WhatsApp. We can go for another Tuesday session next week. That's fine as well. And the session does not need to be 2 hours. If you want a half an hour session, just answer the questions. That's fine. If it drags on to 1 hour, that's okay as well. So let me know when you would like the next session. If I don't hear back from you, presumably it will be about 2 weeks from now, roughly on the so past 14, roughly on the 21st, around that week. I'll try to keep it on a Tuesday because it seems that we're doing pretty well on Tuesday. This is the second session. The last 2 sessions actually today and the last previous session has also been on Tuesday. So people seem to have no problem with Tuesday nights. So we'll keep the Tuesday time. I'm sorry, Khadijato and Anwar, you are in a different time zone. So it's probably the late afternoon for you. Just feel free also to message in the group if the time works for you, and if it's really an inconvenience, maybe you can let know a time that you prefer better, and we can try to work it out with everyone else. But just for your information, it's now 11 p.m. at night for most people, so that's how it is at this point. Yeah. Okay, so final call around the table if there are any questions. Any questions at all? Okay, so maybe I'll just chit chat a little bit more to tell you about the material that is present on the ULearn X. So what this is really is this portion here, the backend IC design tools, is actually showing you how to convert Verilog register transfer logic into the actual transistor level implementation of your standard cells using these open source tools. This is QFlow. This is the process flow here in a PDF file. You can download the Docker virtual container. So it's a Docker virtual container because rather than you having to install the software and all the libraries and all that, what you only do is you install a software known as Docker. It is actually a virtualization software, something like VMware, but it's actually called container technology. It's derived from Linux, and then now it's even running on Windows. What it basically does is it allows you to grab an image of the entire file system, which I prepared, and then you can run it, and then it's as if you're running a Linux machine in your Windows or in your Linux machine, and the software and all its libraries is all installed there. So it saves you the pain of actually installing and debugging the software. I've done that on your behalf. So you can actually pull it up directly from here, and you can follow the video and the instructions on how to play around with this conversion process. But this conversion process is basically to kind of just let you see the flow from actual Verilog code, which we will cover a little bit more in the advanced digital systems design. That's where you will learn how to design circuits with Verilog. So, but once you've got that part done, this is actually the conversion process of how to actually get it in terms of the most fundamental logic gates, the standard cells in your technology library. And way at the bottom here, I'm providing you a link to 2 technology libraries. The default technology library in QFlow is the Auckland State University OSU 0.35 micron technology. So this is a 350 nanometer technology. You can go into the file and you can kind of dig it up and look at the model. So let me see if I can show you an example of that model. Okay, let me do it from this, right? But I'm also providing you a link here, and this link here is actually to what we call a speculative FinFET model. So this is sort of like a inverted commas a fake but realistic model of a realistic model of 7 nanometer standard cell library. So let me show you what that looks like. So just give me a second here. comes under teaching. So this is an example of what that model file looks like. And you can download it at the website links that I've sent you here. These are just gzip files. So you just undo the gzip and you'll be able to get access to these files, right? I just want to show you that the model files, usually they're text files. Okay, this is what they look like, right? So you can actually see sort of the voltage level, the power supply level, the units of the current, and then you actually get the names of the gates. So for example, you will be able to see NAND gate. Okay, NAND gate. Sorry, this is the AO gates. These are the AO gates. This is a 211 input AO gate, and you've got the power, the area, you've got so there's a whole bunch of definitions. This one, each different pin transition will have a different power consumption. And this one's actually the rise time and fall time in picoseconds, depending on the size of the gate, depending on the slew rate, right? So a detailed model like this, this actually comes from the the fabrication house. It's a model that looks like this, and there is a data sheet here. You can actually look at the types of gates, like for example, if you want to look at the simple gates, you can go and look at the HTML file here. Sorry about that. Press the wrong button. HTML source. So the data sheet that I actually wanted to show you is these are actually HTML files. You can actually reference the list of gates that are available. So let me just download this. That. Okay, this is the HTML code. If you find a better way to visualize this than what I'm doing, please let me know. I've forgotten how to do it, but you can copy this and then you can put it in a HTML source. Okay, I can actually save it as a HTML here. Yes, it's a bit complicated, but it need not be this way. It's just not so prepared to show you this as a HTML. So test.html, and then you go to that particular save file, you open it. So there's a nice file like that that's actually showing you this is your 2x2 AND gate. Is giving you the area of the AND gate in that particular units, the capacitance, input capacitance, the leakage power, the rise time delay, the minimum, mid, and maximum propagation delay, the switching power, all of this. So there is one data sheet here for every single gate in the model, right? So that's a Liberty technology file. So here, this is an example of that library where this is, you got a 2x2 AND gate. It's a size 2 AND gate, 2 input size 2 AND gate. Sorry, 2 input AND gate size 2. That means the width is 2 times the length. 2 input AND gate size 4. The width is 4 times the length. The width is 6 times the length. This is a 3 input AND gate size 1. So you've got all these AND gates. You've got all these gates, the majority gates, NAND gates of different sizes, different configurations, NOR gates, OR gates, XNOR gates. So these are examples of what we call the standard cells. They are pre-designed logic gates that come with a library, a technology library. The fab would have already characterized all of this. And actually, there are a few values, a few words here. So AO actually refers to the type of gates. This is the NOR gates. This is those inverters and buffers. That means non-inverting buffers. OA gates, or AND gates. They are complex gates. Sequential. This stands for all those D flip-flops, latches, and all that. And simple, these are the AND gates, OR gates, NAND gates, multiplexers, everything. And then there are two descriptors here. TTSSFF actually stands for the process corner. This is normal, typical process corner. T stands for typical, slow process corner, fast process corner. So when you actually build the logic gates, when you fabricate them, there's a possibility that things could go a little bit wrong in the manufacturing process. So they've actually characterized what happens when the doping, the creation, the fabrication of the logic gates don't go as intended as designed. So this is the far extremes when the gate is actually much faster. That means the current's higher and than anticipated than designed, and the current's much lower or slower. And LVT, RVT, SLVT, this refers to the gates with the design of a different threshold voltage, right? So this is an example of the technology file that I'm sharing with you for you to explore. In practice, you will also get access to this directly from the fab. So if you have a fab that you're working with and the fab is going to give you, you're a customer of that fab's going to really fabricate your chips, you're going to pay the fab for that, then they'll probably give you this technology file and with all the data and the parameters that they've measured experimentally. So that's how it's coming. And the goal here is then to help you to understand how from that model of the fab file that you get from the fab, that all that text file, you can actually convert that into the RC, the resistance capacitance model that you use to estimate the delay. So you can actually just get a parameter there called the fan out of 4 inverter delay. So when you look at the logical effort, that's where we will look at how to do that. You can get a realistic estimate of that delay from that technology and use it to actually do back on the envelope estimation of the critical path of your design. And the wire parasitic extraction is just a little bit more advanced, where after you've converted, the software has actually converted it into standard cells and you've actually connected all the wires together. So the wires, this will involve a place and route step. That means the individual standard cells, the individual logic gates comprising of NMOS and PMOS gates would actually be specifically located on different locations on your wafer, and then they'll be wired up together, right? Certain NMOS must be connected to PMOS. This gate will be connected to this transistor's gate. So there's going to be these wires, right? And these wires will have different lengths. And those wires today actually have an effect because that wire actually has a resistance, has a capacitance. So as you can imagine, taking into account that resistance capacitance also will affect the delay properties of your circuit, also will affect which of your circuit, which of the critical path, where your critical path is in your design, right? Because as you can imagine, perhaps if you just count the propagation delay of all the transistors in that logic, then maybe you find a particular critical path. But after you actually place the standard cells onto the chip, and you've actually started routing them and wiring up together, you will find that maybe the wires would have the dominant resistance and capacitance, so they actually will have a different critical path, right? So this is why it's important to consider the wires. So this is just some stuff for you to explore. Hopefully we'll get around to using them in the problem-based learning. Okay, so any final questions before we part? Okay, so if there are none, then I wish you all a good rest of the day, good night or good evening. Stay safe. Let me know in the WhatsApp. You don't have to wait until the next session if there's any doubts of any of the material so far. Even if we've covered it in the discussion, we've not covered it. If you have kind of learned that far and you have doubts, just let me know, and do my best to address them within a couple of days, right? So thank you, everyone, and stay safe. Goodbye.
Thank you, Doctor.
Thank you, Doctor.